Hello everyone. In this video, I'm going to show you another example for the internal force calculation. Okay, I think you need more example on this because I think you haven't done this much in your freshman year or freshman year. Okay, okay. I think it's not that familiar to you, so I think you need more demonstration. Okay, so that's also a very simple device. Okay, there is a rod here, and this is, I think, it's a pin support. It's a pin support. Okay, the graphic looks like pin support on this bar, and then there's another support BD to support this bar. And in this bar, we have the distributing load on this area. Okay, and then the length under the distributed load is 3 meter, and here is 2 meter. Okay, and then he said he choose section C here. He said, okay, I'll calculate the internal force at this section C. Okay, when this device and this bar under the distributed load, okay, under this external loading. Okay, so and for such problem, okay, we have to use the cut section method, right? Cut section method. And for this problem, I think in previous two video, I think you have a sense. Okay, okay, choosing you can calculate from the right and left or calculate from the right. And so you only need to, the only thing you have to consider is which side is much easier to do the calculation. And for this problem, I think calculate from the left seems much easier. Okay, because if you calculate from calculate from the left, yeah, calculate from the left is much easier than calculate from the right. Because if you calculate from the right, looks like you have to consider the support reaction calculation. Okay, so let's start. Let's cut a section here, and we calculate from the left. Okay, okay, we calculate from the left. Okay, it looks much easier. Okay, but on the left here, the left hand side here, okay, let me see. We have to draw something here. So here we have some information. This is 1 meter. And at this cut section, we can assume it has a shear force, normal force, and a moment at the C point. This we are going to solve. But don't forget here we have a force acting at the B point. Okay, we have force acting at the B point. Sorry, I said I need to use the black. There's a force acting at B. Okay, and he give you the theta. Okay, and this is I call FBD. Okay, so, okay, so do this problem have any information for the BD force? Very sadly, no. The problem didn't give you anything about any information of the BD force. So, if you want to calculate using rigid body equilibrium to calculate the internal force at least C section, you need to know the force BD force. Okay, but how to get the BD force? You have, okay, in the previous video. Okay, well, in the situation you have to do the global rigid body equilibrium, rigid body equilibrium. So you have to do the whole rigid body equilibrium on the whole system. Okay, that's why in textbook it give you this picture right here, because it's just the whole this is just the free body diagram of the whole system. Okay, so okay, let me explain this. Okay, because I don't want to redraw this again. Okay, so this is a free body diagram of the whole free body diagram of the whole system of the whole system of the whole system. Okay, and because like I said, this is a pin support, so it will assume there's a reaction force. So the pin support only create a reaction force, and it's 2D problem. So there's an AY, AX, assume AY point up, AX point to the right. And here he used the he also do the simplification of distributed loading. Okay, there's a distributed loading here. Okay, okay, the resultant force Y is 4.5 kilonewton. Okay, I think I just make a note here. Why is 4.5 kilonewton? Because the resultant force is the area under this distributed load. Okay, so the Fr is equal to 1/2 times 3. And here then it's 3, so it's 4.5. And the position resultant force, because it is a right triangle, so the position resultant force, I think the central is here, and the distance, this distance here is 3/3 equal to 1. Okay. Okay, with this information, after the simplification of distributed loading, then we can do the global rich body equilibrium. Okay, and looks like it's 2D problem, so it's very easy. So summation fx equal to 0. Okay, okay, summation fx equal to 0. What will you get? Okay, looks like, do we have any force in x component? Yeah, FBD cosine 30 degree. FBD cosine 30 degree. Okay, and it's point to cosine 30 degrees, point to the left, so it's negative sign. Be careful. Okay, okay, it's point to the left. Okay, the x component FBD is point to the left. Be careful. And what else? And we have AX point to the right and totally equal to 0. Is this solvable? I don't think so. Okay, let's list another equation. Okay, Fy equal to 0. FBD sine theta point up. FBD sine theta point sine 30 degree and point point up. FBD sine 30 degree and it's point up. Okay, and we have resultant force minus 4.5, but it's point down. 4.5 point down. Okay, and then why we have AY point up and it's equal to 0. Okay. This is solvable. Looks like it's not solvable. So finally, okay, we choose the A as a reference point to calculate total moment of the system. Must be 0. And one thing I have to notice, be careful. The force unit here is kilonewton. So you just make a note here. Make sure you know it's kilonewton right now. Okay, kilonewton. Okay, so okay, let's can keep continuous. So the reference point A, okay, we don't have to consider the moment created by AX, AY. Okay, I don't want to explain it again. And okay, FBD will create a moment. Yeah, the vertical component of FBD, this force vertical component will create a moment. Will create a moment with respect to A. So FBD, okay, but FBD is the vertical component, so it should be sine 30 degrees, sine 30 times sine 30 degree, and it's acting at here. Be careful, it's acting at here, so the labor arm will be 4 plus 1, so it's 4 plus 1, so yeah, it's 4 plus 1, sometimes 4 plus 1. And okay, so the force is point up, okay, and the reference point here, so if they're doing a clockwise rotation, so it's a negative. And okay, 4.5 Newton, this force also create a moment, and it will create a counterclockwise rotation, so you'll be positive, so it's 4.5 and times 1. Okay, and then equal to 0. Okay. Is this solvable? Okay, sine 30 degree. Let me see, sine 30 degree. Sine 30 degree. Okay, sine 30 degree is 0.5. Okay, this should be solvable. Okay, so this 0.5 is 5, so it's minus 2.5. FBD is equal to minus 4.5. So FBD is equal to, okay, it's 4.5 divided by divided by 2.5 is 1.8. FBD is 1.8, but be careful. Right now, your unit is in kilonewton. Let me check that. Let me check my answers. Okay. Okay, yes, the FBD is correct. Okay, so we get FBD. Okay, and then we can use this FBD to calculate interflow force as this C section. Okay. Okay, so let's go back to this again. Okay, once again, use rigid body equilibrium. It's 2D. Yeah, you have to do it again one more time. Summation fx equal to 0. Okay, so FBD and cosine theta. Okay, okay, FBD cosine 30 degree and point to the left. Okay, so and okay, and then we have the x component force is NC point to the right equal to 0. So n for FBD is 1.8. So it's easy to get NC 1.8 times cosine 30 degree 1.55. So NC, I think NC is equal to 1.56 kilonewton. Okay, I think it's the same as the answers. So we initially we assume point to the right, so it's really point to the right. Okay, and summation Fy equal to 0. Okay, so we have the FBD sine theta, FBD times sine 30 degree, and it's point up. And we have VC point up, and we have anything else? No? Okay, equal to 0. Okay, very good. Okay, so what is VC? It's very easy to get VC. What is VC here? VC is 1.8 times sine 30 degree. So VC is 0.9. But now we get a minus 0.9 kilonewton. But the answer is 0.9 kilonewton. I will explain this later. Okay. So finally, what is MC? Okay, what is MC? Okay, M at one moment as C. So we choose the MC as a reference point. Okay, so summation MC equal to 0. Summation MC equal to 0. So okay, FBD sine theta will create a moment with respect to C. So we have FBD times the sine 30 degree. The force is point up and the reference point is C. So point up force, so it will create a clockwise rotation. So it will become a negative. Okay. And then what else? What a moment do we have? Well, no, we don't have considered a moment for VC and NC. That's not, we don't have consider. Okay. And then plus MC equal to 0. So the MC, what we have is, okay, let me check, 1.8 times sine, oh, sorry, we forget, yeah, forget labor arm, okay, but actually it doesn't influence our answer, the labor arm is just the 1, okay. Okay, so what's our MC? Our MC looks like, yeah, what is our BD? Okay, 1.8 times sine 30 degree and times 1. Okay, so our moment, okay, MC moment is 0.9. Okay, kilonewton times meter. Okay, so let's see. Okay, so okay. So and there is a difference between our answer and between our answer and textbook's answer. And the magnitude is all the same, but yeah, there's something happens here. Our VC is minus 0.9, but okay, but answer is 0.9 positive. Why is that? Okay, so that's why I use the next slide to do the explanation. Okay, So here I try to erase these things. So, okay, erase these things. Okay, and then go to the next video. Not the next video, the next slide. Let's go to the next slide. Okay, so next slide, next slide. Sorry, this need the time to clean this. Okay, because like when you check the internal force answer, you have to consider, yeah, you have to consider what's your initial assumption. Maybe the textbook has different initial assumption from you, so that's why you get a little different answer. But that doesn't mean you calculated wrong. Okay, so let's go back to okay, let's go back to this okay slide. Okay, this is the assumption from the textbook. Okay, the textbook also calculate from the left. Okay, we are on the same page, calculate from the left. Okay, but let's see its initial assumption. Okay, its initial assumption is NC is point to the right. Okay, that's the same assumption with us. So we have the same answer on NC. Okay, that's no problem. And look at the MC moment at C. We have the same initial assumption. Yeah, counterclockwise positive. Yeah, so that's why we have the same answer with textbook. But the difference is VC. We initially assume VC is pointing up, and then we get a we got a minus negative answer. So that means the real answer is actually the real answer. The real answer is point down. Okay, the real answer is point down. Okay, and for a textbook, he get the VC is 0.9 kilonewton. Well, why is positive? Because it's already assumed, initially already assumed the VC is pointing down. Okay, and then he get a positive value. That means it's really pointing down. Okay, and our value is minus 0.9 kilonewton. That's because initially we assume it's pointing up. Okay, but we get a negative value. That means in real situation, that means it's really real situation is pointing down. So we get the same answer. We still get the same answer. The shear force at these C sections all point down. Okay, so our answer, yeah, we have a minus sign. This one is different, but actually we get the same answer. Okay, so this is you really have to be careful. Okay, when you're trying to compare your answer for a textbook, you have to know what's the assumption from the textbook. Okay, but if your magnitude is all the same, I think you didn't calculate it wrong. Okay, the minus sign, positive minus sign, that's because your initial assumption. Okay. Okay, so this is also a demonstration of our internal force calculation. I'm hoping you get more familiar with that. Okay, because this is a basic skill in mechanics of material calculation. Okay. Okay, so I'll stop video here. See you in the next video. Bye bye.